Hello and welcome to this video. In this video, we will learn about data types of PostgreSQL. So as I had said that I will go through the entirety of section 2, that is the SQL language. And I have shown some of the table creation elements of which we have discussed various statements like select, update, delete, and some of the alter along with some indexes. So I will start reading through the chapter 8 of PostgreSQL. Let me open it in Ocular. So Ocular will be better. Uh, okay. So chapter 8 is about SQL data types. This is chapter 8. One of the benefits of reading the documentation is that there may be minor points which I might forget to tell if I don't go for a read through. But if I read through, then you can watch the videos. Even you can mute the video and just read for yourself. If your reading speed is faster than me, if you are slower than me, then you will probably have to read the document itself. So I'll recommend that you read it yourself, but in any case, I will read it through thoroughly and I'll explain what is going on. So the most fundamental part of a table is the data type of the columns. And PostgreSQL has a rich set of native data types. Some of these are not available in MySQL or Oracle. There may be different types, and there is a create type command. As you can see, it is on page 1894. We will see create type later on. So first we look at what we have covered. We have covered big int. It is 8-byte integer. The alias is int8. You can type int8 instead of big int. What is it? It is signed 8-byte integer. That is, it will represent values from 8-byte means 1 byte is 8-bit. So 8 is 64 bits. That is minus 4 exabyte to 4 exabyte it can represent. Same is for big serial 8. It is of type auto incrementing. There is a separate sequence is maintained. Then we have bit, which is a fixed length bit string. We have bit varying and variable length bit string, boolean. You have seen boolean. Bit we have not discussed yet. I have not shown any query. Booleans we have seen, logical boolean true or false. Box, which is rectangular box on a plane. These are related to GIS kind of information. Byte, which is binary data. Byte array. Character n. Byte array also we have not seen. Character n. Char n. Fixed length character string. We have not seen character string. We have seen variable length character string. That is character varying var char n. We have seen. CIDR is IPv4, IPv6 neighbor address. We have not seen this. Circle on a plane we have not seen. Date, I think we have seen date or maybe not. It represents a calendar date. Double precision floating point numbers or float 8. These are 8 bytes. Out of these, if I remember it right, 13 bit are for significant and 53 bits are for fractional part. INET is IPv4 or IPv6 host addresses. Integer we have seen, 4-byte integer. Interval is time span. JSON is textual JSON data. JSONB is binary JSON data. Line is infinite line on a plane. L segment is line segment on a plane. We have not seen these lines, or we have not seen interval and JSON or JSONB line segment. MAC address we have not seen. MAC address 8 we have not seen. These are the MAC addresses of your Ethernet chip. Money we have not seen. It is currency amount. Numerics we have not seen. Numerics or decimal. This is exact numeric of selectable precision. Path we have not seen. PG LSN we have not seen. PG snapshot we have not seen. We will probably never use these. PG LSN and PG snapshot. Point we have not seen. Polygon is represents closed geometric paths on a plane we have not seen. Real is float 4. This we can use very easily. You can make use of it. Small int we have seen. Small serial we have not seen. Serial also we have not seen. We have used only big serial. Serial is analogous. Small serial is analogous to serial. Big serial, that is, uh, these are of varying uh, size, 2 bytes, 4 bytes, and 8 bytes. Text, I don't think we have seen. It is just arbitrary length character string. Time comes in two formats: time without time zone and time with time zone, which is time of day. Then we have timestamp without time zone and timestamp with time zone. These are date and time without time zone and with time zone. TS query and TS vector comes in full text search. Those are text search queries and text search documents. We will see this. We have not yet explored these. TXID snapshot, user level transaction ID snapshot. It is deprecated, so we will not even cover it, or maybe we will cover it because it is deprecated. So you might encounter it in your legacy database. UUID is we have not seen. UUID can be used to create primary keys instead of serial, useful in case of distributed database. For example, when you are using with Citus extension, it can be useful. And XML is XML data, which we have not seen yet. So for compatibility, these types are specified by SQL. Big bit varying, boolean char, character varying, character varchar, date, double precision, integer, interval, numeric, decimal, real, and small int, and time, and timestamp and XML. Other fields are not compatible with SQL standard. Each data type has an external representation determined by its input and output functions. Many of the built-in types have obvious external formats. However, several types are either unique to PostgreSQL, such as geometric paths, or have several possible formats, such as the date and time types. Some of the input and output functions are not invertible. That is, the result of an output function might lose accuracy when compared to the original input. So first, uh, the list of numeric types are given. We have small int, integer, big int. The range are given in this size. I said 4 exabyte. It should be 8 exabyte. So this is 8 exabyte, and this is positive part, counterpart of that. So I will not repeat this integer types. I will not. I'll just read it through, but I will not repeat it. The size and incrementing part of serials are given here. Also note that floating points are inexact. That is, what you enter may not get stored. Something smaller than what you enter will be stored, because that's how binary numbers work. Binary floating point number can't get an exact representation in binary of a decimal floating point number. The syntax of constants for the numeric types is described in section 4.1.2. The numeric types have a full set of corresponding arithmetic operators and functions. Refer to chapter 9 for more information. The following sections describe the types in detail. So we read through this section. The types small int, integer, and big int store whole numbers, that is, numbers without fractional components of various ranges. Attempts to store values outside of the allowed range will result in an error. The type integer is the common choice, as it offers the best balance between range, storage size, and performance. Small int type is generally only used if disk space is at a premium. The big int type is designed to use when the range of the integer type is insufficient. SQL only specifies the integer types integer or int, small int, and big int. The type names int2, int4, and int8 are extensions, which are also used by some other SQL database systems. Arbitrary precision numbers section tells us the type numeric can store numbers with a very large number of digits. It is especially recommended for storing monetary amounts and other quantities where exactness is required. Calculation with numeric values yield exact results where possible. Example, addition, subtraction, multiplication. However, calculations on numeric values are very slow compared to the integer types or to the floating point types described in the next section. We use the following terms below. The precision of a numeric is a total count of significant digits in the whole number. That is the number of digits to both sides of decimal point. The scale of a numeric is the count of decimal digits in the fractional part to the right of decimal points. Decimal point. So the number 23.5141 has a precision of 6 and a scale of 4. Integers can be considered to have a scale of 0. Both the maximum precision and maximum scale of a numeric column can be configured. To declare a column of type numeric, use the syntax numeric precision, scale. The precision must be positive, while the scale may be positive or negative. Alternatively, numeric precision selects a scale of 0 specifying numeric. Without any precision, a scale creates an unconstrained numeric column in which numeric values of any length can be stored up to the implementation limits. A column of this kind will not coerce input values to any particular scale, whereas numeric columns with a declared scale will coerce input values to that scale. The SQL standard requires a default scale of 0, that is coercion to integer precision. We find this a bit useless. If you are concerned about portability, always specify the precision and scale explicitly. The maximum precision that can be explicitly specified in the numeric type declaration is 1000. An unconstrained numeric column is subject to the limits described in table 8.2. We'll see table 8.2 we have not seen, I think. Oh, it is here. So numeric is given here. So it is user specified precision up to 131,072 digits before the decimal point, up to 16,383 digits after the decimal point. So your entire precision would be sum of these two. And the precision for floating points are 16 and 15 decimal places. Okay, so that was table 8.2. If the scale of a value to be stored is greater than the declared scale of the column, the system will round the value to the specified number of fractional digits. Then if the number of digits to the left of the decimal point exceed the declared precision minus the declared scale, an error is raised. For example, a column declared as numeric 3,1 will round the value to one decimal place and can store values between minus 99.9 and 99.9 inclusive. Beginning in PostgreSQL 15, it is allowed to declare a numeric column with a negative scale. Then values will be rounded to the left of the decimal point. The precision still represents the maximum number of non-rounded digits. Thus, a column declared as numeric 2, minus 3 will round values to the nearest 1000 and can store values between minus 99,000 and 99,000 inclusive. It is also allowed to declare a scale larger than the declared precision. Such a column can only hold fractional values, and it requires the number of 0 digits just to the right of decimal point to be at least the declared scale minus the declared precision. For example, a column declared as numeric 3, 5 will round values up to 5 decimal places and can store values between minus 0.00999 and 0.00999. So you see here, for example, I'll try to explain. Scale is 1. So 1 decimal digit, and then precision is 3. So total 3 digits. So remaining 2 digits are on the left side. So minus of that and plus of that. Similarly here, your scale is minus 3. So first 3 digits will be 0. These are to the left of decimal point, and then scale is 2. Precision is 2. So 2 and 3, 5. So total 5 digits. So 2 digits which can be handled is 99. So that's how you get the range. PostgreSQL permits the scale in a numeric type declaration to be any value in the range minus 1000 to 1000. However, the SQL standard requires the scale to be in the range of 0 to precision. Using scales outside that range may not be portable to other database systems. Numeric values are physically stored without any extra leading or trailing zeros. Thus, the declared precision and scale of a column are maximums, not fixed allocations. In this sense, the numeric type is more akin to varchar n than to char n. The actual storage requirement is 2 bytes for each group of 4 decimal digits plus 3 to 8 bytes overhead. In addition to ordinary numeric values, the numeric type has several special values, infinity and minus infinity, along with nan. These are adapted from IEEE 754 standard. This is the floating point standard for numbers, and represent infinity and negative infinity and not a number. This standard, if you read, it will also tell you about floating numbers, that is real and double precision numbers, how they are stored. That is also given in IEEE 754. So where were we? Yeah, here. When writing these values as constants in an SQL command, you must put quotes around them. For example, update table set x is equal to minus infinity. On input, these strings are recognized in case-sensitive manner. The infinity values can alternatively be spelled inf and minus inf. The infinity values behave as per mathematical expectation. For example, infinity plus any finite value equals infinity, as does infinity plus infinity, but infinity minus infinity yields a nan, not a number, because it has no well-defined interpretation. Note that an infinity can only be stored in an unconstrained numeric column because it notationally exceeds any finite precision limits. So if you specify precision and scale, then you cannot store infinity. Rather, you should use this notation so that this column type only numeric, so that you can store infinity. Okay, you cannot have a constraint and store infinity in that. The nan value is used to represent undefined calculational results. In general, any operation with a nan input yields another nan. The only exception is when the operation's other inputs are such that the same output would be obtained if the nan were to be replaced by any finite or infinite numeric values. Then the output value is used for nan2. Example of this principle is that nan raised to the power 0 yields 1. So we know that if we raise power 0 to any number, it is 1. So that also applies to nan. But in general, the principle is that if you use nan for addition, multiplication, division, then nan will be, the output will be nan, even though other operands are fixed. In most implementations of a not a number concept, nan is not considered equal to any other numeric value, including nan. In order to allow numeric values to be sorted and viewed in tree-based indexes, PostgreSQL treats nan values as equal and greater than all non-nan values. So this is something I remember that when we were ordering null values were coming to be greatest when we had sorted the value. When you used the order by clause, when we were discussing the tables of, I think, the price, when we were sorting by price, null values were the greatest. So null also you can think in terms of nan. Okay. The types decimal and numeric are equivalent. Both types are part of the SQL standard. When rounding values, the numeric type rounds ties away from 0, while on most machines, the real and double precision types round ties to the nearest even number. For example, select x, round x colon colon numeric as num round x colon double precision as dbl round from generate series minus 3.5 comma 3.5 comma 1 as x. So x is generated as minus 3.5 minus 2.5 minus 1.5 and so on. Now when you do numeric round, it ties away from 0. So minus 3.5 will become 4, minus 2.5 will become 3, and similarly 3.5 will become 4. But double precision types and real types, they tie to nearest even numbers. So this will become minus 4, but this will become minus 2, and so on. Now we move on to floating point types. The data types real and double precision are inexact variable precision in numeric types. On all currently supported platforms, these types are implementations of IEEE 754 for binary floating point arithmetic, single and double precision respectively. This I have already told you that IEEE 754 governs the floating and double types of data type. to the extent that the underlying processor, operating system, and compiler support it. An exact means that some values cannot be converted exactly to the internal format and are stored as approximation, so that storing and retrieving a value might show some slight discrepancies. Managing these errors and how they propagate through calculation is the subject of an entire branch of mathematics and computer science and will not be discussed here except for the following points. If you require exact storage and calculation, such as for monetary amounts, use the numeric type instead. If you want to do complicated calculation with these types for anything important, especially if you rely on certain behavior in boundary cases, infinity command flow, you should evaluate the implementation carefully. Comparing two floating point values for equality might not always work as expected. So here I will add something. So what values can be converted properly to that is exactly to floating point numbers? Those values will be in decimal, where the denominator of the number will have factors only of powers of 2 and only of powers of 2. The reason is our target what you call number system is binary, and binary base is 2. So according to mathematical theorem, if there is a decimal number whose denominator has factors other than 2, cannot be converted to binary. So now that we know any number divided by 2, 4, 8, 16, 32, 64 and so on can be converted exactly to binary, while other denominators cannot be. So for example, 1 by 10 cannot be converted exactly to binary because there is a factor 5 in the denominator of 1 by 10. So with that out, let's proceed further. On all currently supported platforms, the real type has a range of around 1e minus 37 to 1e plus 37 with a precision of at least 6 decimal digits. The double precision has a range of around 1e minus 307. This you can read as 10 to the power minus 307 to 1e plus 308. That is 10 to the power 308 with a precision of at least 15 digits. Values that are too large or too small will cause an error. Rounding might take place if the precision of an input number is too high. Numbers too close to 0 that are not representable as distinct from 0 will cause an underflow error. By default, floating point values are output in text form in their shortest precise decimal representation. The decimal value produced is closer to the true stored binary value than to any other value representable in the same binary precision. However, the output value is currently never exactly midway between two representable values in order to avoid a widespread bug where input routines do not properly respect the round to nearest even rule. This value will use at most 17 significant decimal digits for float 8 values and at most 9 digits for float 4 values. This shorted precise output format is much faster to generate than the historical rounded format. For compatibility with output generated by older versions of PostgreSQL and to allow the output precision to be reduced, the extra float digits parameter can be used to select rounded decimal output instead. You can read about this at page 729. By the way, this is PostgreSQL 17. As you can see here, this is version 17. So once it is updated, the page number will no longer be valid. You have to highlight this by mouse hovering. Setting a value of 0 restores the previous default of rounding the value to 6 for float 4 and 15 for float 8. Significant decimal digits. Setting a negative value reduces the number of digits further. For example, minus 2 would round output to 4 or 13 digits respectively. Any value of extra float digits greater than 0 selects the shortest precise format. Applications that wanted precise values have historically had to set extra float digits to 3 to obtain them. For maximum compatibility between versions, they should continue to do so. In addition to ordinary numeric values, the floating points have several special values. That is again infinity, minus infinity, and nan. So we have already covered this. PostgreSQL also supports the SQL standard notation float and float p for specifying inexact numeric types. Here P specifies the minimum acceptable precision in binary digits. PostgreSQL accepts float 1 to float 24 as selecting the real type, while float 25 to float 53 select double precision. Values of P outside the allowed range draw an error. Float with no precision specified is taken to mean double precision. So I think I'll stop here. That is a lot of content we have gone through, and you might want to revise this by either replaying the video or maybe reading the documentation yourself. That is up to you. It will take a while to finish this fully, because if you see this, this is page number 149 we are on, and we have to go till 219, so that is 70 odd pages. We are on page number 154 and we started at 148, so 5-6 pages if you average, then it will take probably 10-12 videos. So now where are we? Serial types. Okay, so serial types will be the last of, let's complete serial types. That will cover numeric types. So I will cover this serial types and then we will stop here. So serial types. This section describes a PostgreSQL specific way to create an auto-incrementing column, and another way is to use SQL standard identity column feature as described at section 5.3. The data types small serial, serial and big serial are not true types but merely a notational convenience for creating unique identifier columns similar to the auto-increment property supported by some other databases. In the current implementation, specifying create table name, column name, serial is equivalent to specifying create sequence table name underscore column call name underscore sequence as integer, create table name column integer not null default next val table name underscore call name underscore sequence, alter sequence table name underscore call name underscore sequence owned by table name dot call name. Thus, we have created an integer column and arranged for its default values to be assigned from a sequence generator. A not null constraint is applied to ensure that a null value cannot be inserted. In most cases, you would also want to attach a unique or primary key constraint to prevent duplicate values from being inserted by accident, but this is not automatic. Lastly, the sequence is marked as owned by the column so that it will be dropped if the column or table is dropped. Because small serial, serial, big serial are implemented using sequences, there may be holes or gaps in the sequence of values which appears in the column, even if no rows are ever deleted. A value located from the sequence is still used up even if a row containing that value is never successfully inserted into the table column. This may happen, for example, if the insertion transaction rolls back. See next val in section 9.17 for detail. To insert the next value of the sequence into the serial column, specify that the serial column should be assigned its default value. This can be either done by excluding the column from the list of columns in the insert statement or through the use of the default keyword. The type names serial and serial 4 are equivalent, both create integer columns. The type names big serial and serial 8 work the same way except that they create big int column. Big serial should be used if you anticipate the use of more than 2 to the power 31 identifiers over the lifetime of the table. The type names small serial and serial 2 also work the same way except that they create a small int column. The sequence created for serial column is automatically dropped when the owning column is dropped. You can drop the sequence without dropping the column, but this will force removal of the column default expression. So with this, we will end here. We have covered all the numeric types. In the next video, we will cover monetary types, character types, and possibly binary data types. It will be too much. So let's see, we will cover half of binary types, byte array hex format we will cover. We'll see character types is quite big, 3 pages, and then yeah, we will cover monetary types, character types, and binary data types in the next video. So I hope that you are enjoying this read through and are finding it useful. When I read it again, I remember a lot of concepts which I have forgotten earlier. For example, the concept of raising nan to the power 0, uh, I did not remember. It refreshed my memory that it will be equal to 1. So lots of things are refreshed for me also. So if you watch these videos with patience, you will learn a lot. And at the end of this entire chapter, I will show you how to create columns of every type discussed here. Okay. Some of these are unique in the sense that for UID, I believe you need to create an extension. Um, yeah, I'm not sure. Create extension OSP minus UID is needed, but we'll see if this has become native. Okay. Earlier we had to use possibly an extension, but maybe 16 or 70 change it. I don't know. So let me know what you think about this read through in comments, and I'll try to reply to each comment to the best of my ability. So thanks a lot for watching. Happy programming.